Hello, please welcome our next presenters from Heuristic, Gabriel Goyx and Maximo Lambruschini. They will be talking about production scheduling tools for metal meshes in their factories. Welcome, Gabriel and Maximo.
Oh, hello. Thank
Hey
you very
everyone.
much. Hi everyone, welcome. Today we'll be talking about a project in which we developed a tool to optimize the production schedule of the metal meshes factory. I'm Gabriel, partner and director at Eurystic, and joining me is Maximo, senior consultant also at Heuristic. First, let me briefly introduce ourselves. We are Heuristic and we develop high-impact solutions to complex problems. We seek to help companies continually improve their operations using the latest and analytical methodologies, allowing them to make a leap in quality and performance. We mainly develop software and provide consulting services using robust quantitative support that is applying modeling and simulation, optimization algorithms, or machine learning, some of these or a combination of these, depending on the problem to solve. Although we don't exclusively work on supply chain projects, we do have vast experience in manufacturing, transportation, and warehousing operations. And all the tools that we developed are tailor-made to solve the client's specific problems. So without further ado, let's dive into the project. In this case, our client was a large steel manufacturer that produces a wide range of products. And in this case, we focus on a part of the plant that manufactures welded metal meshes and also drawn wire. There are mainly three processes involved: cold rolling, bending, and welding processes, and a lot of machines across this process work together to manufacture these products. Raw materials come in and go through the cold rolling process, and the products that are made there can be directly prepared as drawn wired and can be shipped to the clients, or it can be used to feed the bending and welding processes to ultimately manufacture metal meshes. To move materials from and to each of these processes, there are important constraints to consider because many of the intermediate and final products must be put in containers that are available in limited quantities or in buffers with limited capacities. This factory runs mostly under a make-to-stock policy, and thus it is critical to have a good demand forecast and a balanced production schedule to guarantee a diverse product offering. So now that we have established how the overall process works, let's look into the problems that the factory faced that caused the need for this project. First of all, the production scheduling was carried out manually by the planning team using spreadsheets. So it was really difficult for them to take into account all the aspects involved in the production scheduling, such as the machine calendars, the maintenance, the raw material availability, the resource capacities, and among others. And as the resulting schedules could not be strictly detailed, floor factory staff had to make local decisions to optimize production, but this resulted in an overall low productivity in the long run. Also, given the nature of the products and how this market works, the clients usually for a certain mix of different products, and if they can't find the whole mix available, they will probably turn on to another supplier. On the other hand, given the high setup times of the machines involved in this process, from a productivity point of view, it is best to continue to produce high quantities of the same products for long periods of time. But following that production pattern will probably cause for the storage area to be filled with only a few different products, possibly slowing sales. And that would probably cause the storage areas to collapse and halt production, and the planning team had no way to anticipate these kind of problems. So, given this context, the client was looking for a tool to provide support for the production scheduling process, and the overall objective that they set was to maximize service level and align production with the sale forecast, but also while considering production efficiency and resource utilization. So we basically have two competing strategies. One is commercial prioritization versus production efficiency. And the tool had to produce a schedule of a horizon of at least 1 month and take into account all the components in the system, such as the machines, the buffers, the transportation means, all the containers, all the calendars, and many more. So we proceeded to develop a solution for the client's needs. We determined that the solution required a simulation model to represent the system because it must include many complex components that interact with each other, and it also evolves in time. Many of these components, such as the machines, share limited resources, and some buffers have particular storage logics. These characteristics make it difficult to model the system in another way. And we chose AnyLogic because it provides an overall great development experience. It has an intuitive user interface and reduces the time that is required to develop a simulation model. Also, the team has a lot of experience with AnyLogic and Java. In fact, some members of the team are teachers at the university that teaching simulation using AnyLogic. So to develop this tool, we had to take into account a lot of information and parameters. Most of the inputs had to be flexible enough to allow the client to try different scenarios. So we had to consider all the machines with their calendars, the setup times, all the products, all the storage areas and the transportation resources with their limitations. We had to consider not only the forecasted demand, but also the confirmed demand that have a different production strategy. Another key aspect we had to take into account is the raw material availability that limits at which point in time you can manufacture certain products. And as this tool can be run at any point in time, it has to be able to capture the system's current situation. That means taking into account the initial stock, what type of products do you have available right now, in what quantities, and where is it located. You have to consider what the machines are currently producing, and also we allow the user to input a predefined schedule for certain machines, and that allows them to have more flexibility. So going into the model, at the heart of the tool, we find the simulation model. This allows us to represent the system with enough detail and precision to capture its dynamics, which helps to make an accurate prediction. The model was developed using an agent-based approach to maximize flexibility and represent the nonlinear interaction between the different components. The most complex components are by far the machines, that include large stagers that monitor and control their behavior. And they also include inner heuristics to optimize certain parts of the process and adapt to changing context conditions. Storage areas were also represented as individual components because they have important constraints and particular storage logics that are required to accurately model the system. So to find an optimized production schedule, we developed a custom optimization engine applying local search heuristics and meta-heuristics such as taboo search. This optimization engine runs independently from the simulation model and, in fact, uses the simulation model to test different solutions. Once the input is read and all the parameters are set, the construction phase of the optimization starts. First of all, it triggers multiple simulation runs using a construction heuristic with different production strategies. These different production strategies are basically variants of the heuristic covering a range between favoring commercial prioritization or production efficiency. Each of the simulation runs is run until the end, and then it can compute the overall result using an objective function that mainly takes into account the covered forecasted sales. After all these initial simulations are finished, the production schedule that yielded the best result is then selected and used as a starting point for a local search algorithm that looks for a better solution. At this point, the search phase of the optimization starts. A multi-threaded approach was chosen to run the simulation, while a main thread controls the execution, triggers new simulation runs, and guides the exploration. This optimization engine adds simulation to an execution queue, and each of these simulations have the instruction to follow a certain schedule. So when a new thread frees up, it picks one of the pending simulations and runs it until the end to compute its result. The simulation not only returns the result, but also a set of limited and filtered alternative schedules that are similar to the instructed schedule. So this is picked up by the optimization engine and uses these alternative schedules to keep populating the execution queue. And the return result is used to compare to another schedules, guide the search, and finally pick the winner schedule. So Maximo will now present a video showing the interface of the tool.
Okay, so as Gabriel mentioned, we needed a tool that could run the simulation multiple times in order to pick the best possible scenario. In order to do this, we developed from the ground up a Java desktop application that included the optimization algorithm, the simulator, and the UX made with JavaFX. Now, well, as Gabriel mentioned, we're going to show a quick video demonstrating the UX of the application and how the information is displayed. So here in the control panel, the client can select on the left the desired scenario to optimize. Then on the right, the client can set some parameters for the simulation, such as the optimization horizon, the storage criteria, production criteria, etc. Once you run the optimization, something important to mention is that all the results showed here on this dashboard are all invented. They're not the real values. They're just for this example. So once the dashboard is presented, you can see the covered demand, like meshes and the cold wire covered demand, the machine utilization for the cold rolling machines, bending machines, and welding machines, warehouse utilization for meshes, cold wires, and the backup warehouse, production in tons, and there's also the possibility to export the results by pressing the button on the top right corner, which says export results, and this will export the results in an Excel file, in the form of an Excel file. So now, moving on to the schedule section, here on the welding schedule section, the client here can see the production schedule for the welders, in which there's a table which will say what material must be produced, looking at the first two columns. Then on the third one, the quantity in kilograms, and on the last one, the last two columns, the start dates and the end dates of the production. This same information is also presented in the form of a Gantt chart, which shows the production times of all the materials that must be produced to follow the schedule, and also if there's a time where there's no material being produced, and also if any machine needs to do a setup, it will show the setup times. Now, moving on to the machine performance section, here the client can look at some key performance indicators on the left, which show a table with for example, the available time in hours, maintenance time, setup times, net operating time in hours also. And on the right, there's two charts, one showing the production by day during the simulated period, and the one in the bottom shows the efficiency by day. Now, going into the containers and storage section, more specifically the warehouse, the client here can look at some global indicators on the top, like the available units, the average usage of the area of the warehouse, the average usage of the floor positions, and the volume. On the left, there are some histogram charts showing the usage of the area and the volume, and on the right, the evolution of the usage of the warehouse during the simulation. Now, going into the stock section, here the client, by selecting a material, the tool will show three charts. The first one on top being the amount of material entering the warehouse, the second one, the amount of material exiting the warehouse, and the last one showing the available stock on the warehouse at that point, and the amount in gray, the amount of stock in quality control. Now, moving on to the last section, the raw material requirement section shows a table displaying the amount of raw material needed to follow the production plan calculated by the tool. and this information is showed in the form of a table on top, and also the same information is displayed in the form of a chart on the bottom, which shows in different colors what type of materials are needed. So now, if we go back to the presentation, there we go. The developed tool runs as a standalone desktop app that reads all its input from Excel files. A great part of the information in the input files is taken from SAP and processed by the tool. And when the optimization finishes, the tool not only displays all the results as KPIs and charts, but also allows the user to export them in Excel files. This allows the user to carefully analyze and compare the provided solutions. The exported machine schedules are prepared in a format useful to be easily loaded into SAP and launched to the factory floor.
Okay, perfect. Thank you very much, Maximo. We will now look into the achieved results of this implementation. So far, we registered a 10% increase in production, and even more is expected as the factory staff continues to embrace a new way of working that was proposed along with the implementation of the tool. And also, let's take into account that this implementation took place in the middle of the pandemic, and it is expected that the performance continues to improve as the pandemic situation begins to stabilize. In fact, production has risen to a point in which the system's bottleneck has shifted to the outbound transportation sector, and we are currently working on a project in that sector to improve the operation. The tool also has enabled the client to make important strategic decisions. For example, it enabled them to assess the operational impact of manufacturing certain products, and even decided to discontinue the ones that were not convenient. The tool also has partially automated and greatly reduced the time required for the production scheduling generation process, and from a process that took several days to have a polished version to a system in which they can achieve a schedule in a few hours or even less. It also provided a way to predict and anticipate potential problems, such as the one we talked about of warehousing saturation, and taking preventive actions to avoid them. And also having a way to accurately forecast production and the system's evolution has enabled the planning team to improve the coordination and the communication with other sectors. For example, the sales teams can now rely on accurate predictions and better align clients' expectations. The logistics and transportation teams can now adapt its resources to prepare delivery schedules. Machine maintenance can be scheduled when most convenient. And finally, as it allows to anticipate the raw material requirement, this can be in turn be used to schedule production in another processes from another sectors of the factory. So that's it for the results, and we will open now the Q&A session. Thank you very much.
Okay, so how were you able to connect the simulation model to this tool? Okay, so in order to connect them, you must export the project, the AnyLogic project, and then you must import it to the Java, in our case, the Java development environment as an external library, and then you can run it multiple times.
We used this approach. Okay. Why do you use a simulation approach, and did you compare this option against a plain scheduling tool? We chose this option because it is a complex system, and we tried other possible solutions, but we found it difficult to represent all the components that we wanted for it to take into account. The other things we tried were not as satisfactory in the results, and had to be oversimplified in certain aspects. Is your model considering yield and scrap? It is considering it considered in the production and in the bill of materials of the products that are taken into account in the system. Okay, about how did we gather the data? We worked along with another consulting company and a lot with the client to take into account all the inputs. The client in this case uses SAP, so they are a lot of information that we had to process a bit to determine certain parameters and for example production efficiency, but most of the information was already there. How is the simulation model maintained during operation? All right. I don't know exactly what this means, but we are currently working with the client to continually bring support to their production scheduling processes, and if they have the need to update it or modify a part of the simulation model, we are available for them to help them. Yes, the setup times. To the question that if we consider setup times, we did consider setup times, and they are really important because these type of machines have high setup times, and to change from producing one product to another, it takes a lot of time, and this really affects the performance of the system.
Any more questions, anybody?
The heuristics was okay. To the question that how did we set up the heuristics? The heuristics were defined with the client. It first took a great effort to understand all the problem, how the factory works, how each machine works. Some of the machines work in batch ways. So once we understood how all this works, we held several workshops with the client to talk about different possible heuristics until we finally found one that made sense to them and that was a pretty good starting point for the local search algorithm. The project took about 6 months, but let's say take into account that this was implemented and developed in the middle of the pandemic, so we had a bit of a break in the middle. But overall, it was about 6 months since the kickoff meeting until the tool was already working and usable by the client. Working about 2 persons, more or less, along all this process. Okay, there are no more questions. Thank you all very much for your attention and have a good day.
Everyone.
Thank you so much for that, Gabriel and Maximo. We actually have another team from Eurystic coming up next in just a few minutes. So stay tuned. The presenters will be Damian Marino and Alejandro Paz. So please stay tuned.